Cool. So I'll start off by an observation. I've been looking at like when I first saw the lineup of the talks, I thought that it's perhaps on point because of the current climate of gloom that we are in. It's an afternoon of negative feelings like test is dead, we've been doing security wrong, SaaS tools have failed us, there's a dumpster fire. I thought that this would be a very despondent afternoon, which is again on point. But then I've been listening to the talks. I was almost missing this talk because like there was a couple of fantastic talks that was before this, and there's a whole lot of stuff that are takeaways. So here's my takeaway on how our SaaS tools are, and we have a general feeling of how our SaaS tools are. But let's try to quantify those feelings, and let's understand like how does that impact our decisions of how to consume the SaaS tools. So a little bit about myself. I probably need to update my resume. I've been working at security, like static analysis and automatic bug detection and fixing for about 20 years now. So not 15, but perhaps. So I need to update. So I call myself a one-trick pony, and I've like back in the 2009. When I did my PhD, it was the first work that asked the question, why stop at detecting bugs? Like, why our SaaS tools were just detecting bugs? Why can't we also automatically fix bugs? And at that point, this was the first work that in the academia that was asking that kind of questions. Then I went ahead and built tools. I was in the academia. My students and we built the first tool that was looking into general purpose problems in C code. Specifically, we were looking into integer overflow, underflow, signedness, and witness related vulnerabilities. We built a tool in the academic research that particular work actually was awarded as the best computer science research in all disciplines of computer science in that year. Here you see my student getting awarded at the Turing Award ceremony in 2013. Later, I've also worked at Coverity, which is one of the leading bug detection tool companies. I was responsible for the first commercial bug detection tools in JavaScript and Android. And then I started a company which is looking into static analysis tools and SCA, specifically the application security space. And here we are. So I've gotten lots of experience. I think I know one thing or two about static analysis tools. And here's a general observation of, in general, like what the static analysis tools provide you. And there are three cases where they fall short. Number one is we talk about lot of false positive, and that's definitely a problem. But the main problem is that the static analysis tools miss critical bugs. In fact, industry data has found that only about 14% of the bugs are detected by all tools, and that includes fuzzing tools and other tools as well. The remaining bugs are detected by pure luck, as in by observation that something is being breached, or just by like manually stumbling upon that. No tool was used during that kind of discovery process. So 100 bugs out there that are being published every week in the CVE, we are probably finding only about like 14 of them or 14 or 15 of them from using static analysis tools. So there's a big gap there. Like when we talk about static analysis, the first thing that dominates is there's a whole lot of false positives, but then we actually miss a lot of bugs. Like for example, Coverity was used with OpenSSL all the time during the period of 2012 and 2014, but it was never able to detect the heartbleed bug. The bug was found when it was found, and that created the whole industry about 500 million, cost the whole industry about $500 million. So our static analysis tool Coverity, which is the best in class in C++ analysis, was not able to do anything there. Then there is the issue of false positives. There's like 90% false positive is pretty common in static analysis tools. So every 10 bugs that you find, 9 of them are not a bug, and somebody in your engineering team has to triage that and identify that what among all my findings, which ones do I prioritize and fix in the first place. And then even in 2024, there's still not enough, or like there's a few manual, there's a few like automated fixing tools that are around, but none of them perform, or majority of them do not perform very well. So most of the work is still done by manually fixing bugs, and it has been documented many times that this manual fixing reintroduces errors. So we have this feeling in our underbelly about static analysis tools missing a lot of bugs and also having a lot of false positives. But we don't have data that we share around or tell others uh, uh, often enough to validate that, and then use a set of data that can be used to universally judge multiple tools when they come like when you're buying a tool, you need to have access to there's already the POC that you're doing, which is like running it on your code, but at the same time, like there should be this kind of benchmark data that is available. So I'll share a little bit of work that I've done in this area. So I have this video series that I've been posting on YouTube. I call it Test Drive Your Bug Detection and Fixing Tool. Uh, Basically, the premise is very simple. I take a static analysis tool, I run it on some open source application, and I review the result. Do that, all of that in a very short amount of time, in a very condensed amount of time. So there's a whole lot of pre-production work that happens, and then during the video, I typically show the bugs in the bugs that have been found, whether they're true positive, false positive, etc. What do you do? So in order to do that, you need to run it on a uniform software. So in order to get an idea of like how the tools are across the board. So here I've done some work on running all the static analysis tools on Kubernetes, which is in Go, most prominent Go open source tool that's out there. And so that's about over 1 million lines of code. So it's significant. So therefore, it's very interesting to find what our static analysis tools are in general finding on this, and getting a sense of that result. So here I'll show 4 different tools and what did they find in that. But before that, I did not use the current repository. I used a specific repository. The repo link is there on the left. And I promise you that these QR codes are good and they're sanitized. But that particular Kubernetes version was selected because it had 2 known data races, like one data race and one double locking error in that, and both of those errors are currently have been reported and are being fixed right now. The links of the issue are also listed here, but essentially this is giving you an idea of a specific application, a significant application on which we'll be running 4 different tools. There are 2 known bugs there. We'll try to understand what kind of bugs are these tools finding and whether they're finding these known bugs. That's a very simple premise. So here's the first tool. The first tool is CodeQL. We found out that it reported 23 bugs. There were 2 true positive or true positive-ish bugs. That is 2 bugs that required more attention from the maintainers. There were 5 won't fix issues. There's 16 false positives, and then the 2 bugs that I identified previously, and we knew that it's there, they were not found. So we have a simple metric where we just think that for triaging each of the bugs will just take 10 minutes. So that means that it'll take us about 4 hours to consume this result by somebody. And we are assuming that about $130 is the loaded labor rate for doing that particular work. So that is costing us $520. So I'm just using this metric. You can argue about the labor rate, about the time it requires with the founding. That's requires to triage the bug. That's not the main point. The main point is it's creating a uniform metric in order to find out, in order to give you like what kind of bugs are found. So let's look into the two true positives and or true positive-ish. I call it true positive-ish because here, like they're the true positive, the two bugs that were identified as true positives by several tools. They were identifying it on cases where there is an skip verify, insecure skip verify has been configured to be true, but it should be configured to be false. So uh, we should not like have this thing as true. And that's bad, but it might be required for many different reasons by this specific product. So we don't necessarily have that information. So it's a good idea to involve the maintainers here and get their take on whether this is a vulnerability in the first place, or this is something that we need to care about. So that's why I call it true positive. It requires another attention, but we cannot just say like this is true positive. So CodeQL found two such things, and we worked with the maintainers. We found out later that they're intended, so that's okay. But at least these are some useful stuff that you may need to look into again. Um, as far as false positives, there are many false positives that were found. So one of those were like CodeQL was reporting that there are many hard-coded secrets, and it is actually taking many of the magic strings that are used. Those are not secrets. These are just like general, probably because they had like the variable names had username in that. So naively, CodeQL was understanding or thinking that this is probably a username which is probably insecure, and that's how underlyingly these tools work. So that's why like these kind of things were detected. They're not bugs, they're not interesting, they're all false positives. So here's the data. So that's in general, give you a sense of like what CodeQL is finding in there. Let's look into another tool. Now let's look into SameGrep. So SameGrep reported 157 of them. There's again 24 of them that are true positive-ish. So they're not necessarily true positive or bugs that you can just look at and say like, okay, this is true positive, this is what I'm going to fix. But these are again stuff that require maintainers' attention. There's 57 won't fix issues. These are bugs in the test code or very minor bugs that you don't care about. There's 76 false positives, and still the two bugs that we knew that were there were not found. And again, looking at the hours, it's more because more bugs were reported, and therefore the cost is also more compared to the others. And for this, I have so for all of these, I have the data link that shows on the left, like there's a link to the data where these data are available about what exactly those findings were, and specifically like what categories of bugs were they found and why were they categorized as false positive, won't fix, or false negative, etc. So that data link is available. I also have the video for this, the CodeQL, that's a video that I'm doing right now. But for this, there's a video that will show you basically a walkthrough of these results. Again, the insecure skip verify was found here. SEMGRAPH actually found more of these, but some of these were false positive. So it found more than what CodeQL did in Kubernetes, but some of them were false positives for different reasons. And there are also false positives that were found, like there's an iteration over an empty map, which was confusing, and it wasn't a true positive bug. So that's kind of like what the results are. Let's look into another tool. Now, I'm talking about Snake, again, a very well-known tool. It identified even more, 378 bugs. There were 13 true positives, again, true positive-ish. There are 235 issues that were won't fix. There are 130 false positive issues. Still, the two bugs were not found. And there's like more time is required in order to do that. Like in order to triage these bugs, and therefore it costs even more. what kind of bugs did we find? Again, it's the same kind of bugs. So that's a good thing, that across the board the tools are finding the same kind of things. At least that's an assurance. But then Sneak here reported a few that are again like true positive-ish, but then in sorry, uh, there are few that are true positive-ish, but then there were also others that were false positives because won't fix issues, because they were found in test code. So at least the tool should filter that out, that this is in test code, this does not require us to look into that. So the final tool that I looked into is Sonar Cloud. Uh, it went off the chart. It found 16,244 issues. There were zero true positives. There were 16,244 won't fix issues. Thankfully, there are no false positives, but it's won't fix or stuff that we don't care. And that bug was also, those two bugs were also not found. Clearly, there's a whole lot of like this is like we will not be triaging these many bugs. Probably if this is the case, then we'll just leave them around and probably not come back to them. But just for the heck of it, I'm just giving you the numbers just so that they're in the same on the same page. So why were there so many bugs that were found that were false positive? Basically, it was finding like duplicate constants, which is a good thing to have, perhaps, but it's not something that is related with security. It's not like in many cases these are left unfixed. So that's why we were telling them as won't fix. And even if you want to fix these, then like doing this thing like 7,000 of them would require some endeavor. So it depends on the risk profile that you want to have in your like application. But clearly this is not a security bug, so it probably would not be fixed or remain unfixed like this. So bottom line, what we're seeing, what are we seeing? We're seeing that there's a whole lot of tools that are out there that are reporting a whole lot of stuff. But coming back to that point, that the real bugs or the hard to find bugs remain hard to be found, and they're just not found. And these false positives, they're just creating busy works for us. So how has the industry wrongly tried to address the SaaS capability? One way is to use multiple tools. That's kind of funny. So you are basically our approach to handle false positive from one tool is by using multiple tools and hope that they take care of each other. And that has now like creating these aggregate platforms where there are multiple tools and they're cross-referencing the data and so on. I feel like that's one of the drivers in the current industry trends that we are going on. But it's clearly like trying to hide the tools with others, and it's not really helpful. Then there is, of course, the default thing that you do in 2024. You just summon AI. And there's a few tools that are out that are trying to fix stuff with generative AI. But these tools are often producing fixes that are wrong, or producing fixes that break the code, or actually claiming that that there are code stubs that are remediation advice at best. Just putting this in a diff and showing it with red and green color does not mean that that is a fix. It's not going to fix this SSRF problem here. So having that kind of like I was at RSA earlier this year, and one of the things that was surprising is everybody was claiming that their tool was doing AI fixes, and upon looking at them closely, what they're generating is just code snippets that are automatically generated, that are not diffs. You cannot apply them to your application, but that gives you a code snippet that like basically shows you code that are already described by your remediation advice. So it's just codification of that. It is actually not a fix. I've seen that kind of rhetoric has lowered a little bit when we have come into Black Hat, but that's interesting. At least the industry is coming to correct that. So throwing AI at everything is not necessarily the solution. We still haven't found the good edge to that yet for that. But at the same time, AI is not bad. AI is wonderful. Like this was going like just 2 days ago. We found this report, or many of you probably have seen that Google is claiming that they have this agentic architecture that identified the first zero-day security vulnerability. It is a security, but Google was not doing it as the first company for doing that. There was a competition in DEF CON earlier, organized by DHS. It's called AIXCC. There was a team called Team Atlanta that actually identified a null pointer dereference in SQLite code, which was zero. I mean, if it's null pointer dereference, you cannot probably call it 0-day, but it was not found by anybody else. Well, this is a buffer overflow vulnerability that Google found in the same vein of research where you use an agentic architecture and do and basically try to detect bugs en masse. This is not necessarily when I look deeply into it. I mean, I because this is so new, I thought like I needed to share that about something that AI is doing that would not necessarily modifying the SAST tools now, but should be something big in the future. So here you have a data structure. On the left, there's a structure, there's a field in that called I column, which is an integer. And this value, because it's an integer, it can take positive and negative values. But on the code in SQLite, in line 705, there is a like that I column is being used, and this could be a negative number. And if it is a negative number, this would create a like bad memory read, bad memory write at a particular point. And in debug mode, there are asserts that allow you to check that, but you don't have that in release mode. So therefore, in release mode, it becomes a buffer overflow issue. So in this particular case, when I looked into the architecture deeply, I found out that it's an agentic architecture that is actually based on more like fuzzing technology. They do have like static analysis components on that, but this particular thing is not necessarily found with static analysis. Nevertheless, I feel like static analysis and AI need to work together, and static analysis tools should provide precision, but it should work like not just by asking LLM to fix this bug for me or do something, and then the LLM, whatever it provides, just putting it back um, to the end user. I feel like that there should be a hand holding where the static analysis tool should still be the driver and it should bring in the precision, whereas the AI should leverage upon the summarization and the generation capability to do wonderful stuff that the static analysis tool would otherwise not be able to provide. So coming back, like what this gives us is when we look into our static analysis tools, we need to talk about metrics. We need to demand that when vendors come to us, they need to provide us metrics. And one metric could be providing this false positive and the true positive score on known benchmarks. Like this is the like the NIST created Summit benchmark, which shows like tens of thousands of programs in Java, C, and C++. So it's specific for that particular case. But you can look into even like specific vulnerability capabilities. You can ask for data about like whether certain kinds of vulnerabilities are being reported or detected or not. What is the true positive rate? What is the false positive rate? Because it's a benchmark, it will allow you to calculate those data. So that's definitely a great thing that you need to demand. At the same time, the percentage of bugs that actually result in a fix, that is a metric that like we should also use the benchmarks in other cases where benchmarks are not available, like in languages like Go or Python or JavaScript. We can use applications like this Kubernetes, known applications like the top 10 open source applications that are for that particular language. Having that data available by all vendors would definitely help. The percentage of bugs that actually result in a fix is an important metric here. Counting the won't fix cases, counting the false negative cases also matters, because what you can do is when you are running a tool on a specific version that was in the past, and you know that there are CVEs that were reported on that particular uh, particular package in the future, what happens, or in between, like the past and the current time, what this means is that when you run the tool on that particular application, some bugs were missed. So when we are running these things on open source applications, what are the false negatives, what are the bugs that are being missed? I think that there should be some demand of those false negatives being reported, and these frankly become a good tool, good things for the tool vendors to fix in the first place. And then also the quality of the remediation advice. Did the remediation advice also help, and so on? So coming back, the key takeaways for this is that the signal to noise ratio is awful for SaaS tools. This is even in 2024, after 30 years, actually close to 32 years now, since the first static analysis tool was built. But still, the signal to noise ratio is very awful. That's just sad. And but static analysis and AI, that's the next thing next thing that's coming. It should be, the AI should be used in a responsible way, so that it goes they work hand in hand and actually provide good results rather than more hallucinations. The SaaS tool should be explicit about the capability against their benchmarks, and the SaaS metrics should be measured and shared by research community and vendors. Those are stuff that we can collectively start creating a demand, because otherwise, like, we are all living in this own echo chamber of things where we think our tool is great, but we don't know how great or how good is it against others. So that's basically the key takeaway. I'd be happy to take questions. So I can't see the chat. If anybody can, like, if Oscar, you can help me identify if there are any questions. Otherwise, I'm good. Thank you. Thanks, Josh. Yeah, the problem why where this is going to take us is, like, we are already, like, there was a great talk by Kyle about the supply chain security, which is the biggest security problem in our time. And yes, not all the security problems are reachable, but the main and that's one of the things that is marring the SCA results. But one of the big things also is that with the software composition analysis, this whole idea is reactive. I mean, we only see an SCA signal after a CV is published. There's no, like, proactive approach of going and trying to find the security problems in the first place. And the reason why the SaaS tools could come useful here is they can allow you to do this proactive scanning. But wait a minute, our SaaS tools are even struggling to give us good results for our one application that we are building, one proprietary application. What about the 1,000 dependencies that are consumed by that one application? So that is the fundamental problem where everybody, all of us, are heading towards. And unless the SaaS tools become better, or if the SaaS tools become better, then, or when the SaaS tools become better, there is an opportunity for us to have a stab at a more proactive SCA, which is something where SCA also needs to go next. There's a whole lot of dumpster fires that are out there. It's a great point. So it depends on it depends on the risk profile. So in many organizations that we see, that there's the medium and the low bugs that are, well, specifically the low bugs, they're almost never fixed, but in other organizations they are there. So yes, you're right. Like, it might be a responsibility for the tools to show all and then have people decide. But at the same time, majority of the stories that I hear is, I just tune out, because so either I dial and ignore the low ones anyway, or we don't pay attention, which is even more dangerous. But I'd be happy to discuss. offline on this. Okay, I think that's it. Thanks a lot.